Hello everyone, my name is Namit. I'm a machine learning researcher at Cura. Today I'm going to be presenting our paper on effective transfer learning for identifying similar questions, and specifically how we applied it to matching user questions to COVID FAQs. This is joint work with my colleagues at Cura and Clara, who interned with us last summer and is currently pursuing graduate studies at Stanford University. People have been increasingly looking to the internet for information related to their health. With COVID-19 and lockdowns, this has only increased in the current times. More broadly, the rate at which medical questions are asked online far exceeds the capacity of qualified doctors to answer them. However, there is bound to be a large amount of overlap in these questions. Therefore, a reliable identification of similar questions would enable better usage of resources. A rapidly evolving situation such as the present has led to several institutes such as CDC, FDA, and digital media like New York Times publishing FAQs. However, there are several challenges for end users. There's a lot of easy to spread misinformation out there. Second, it is hard to get answers to specific problems and navigate pages with many FAQs, like the one shown in the screenshot on the right. And lastly, with a doctor, if your question isn't answered or isn't answered adequately, is not easy, since in-person visits are impractical given the current times. Our solution to this was an automated question answering tool to map the user question to curated FAQs. So as you can see in the screenshot, the user can type in free text questions. And if there is a match that we find within our curated set, we show them to the user. Because our platform Cura Health offers users ability to chat with doctors, we also allow the users to address any unanswered questions or concerns they might have. This also applies when we do not find matches in our curated set of FAQs for the user's questions. In that case, they can just continue and talk to an actual doctor. Moreover, since the answers can be vetted by our doctors, we can be sure that the information that gets surfaced to users is trustworthy. Next, I'd like to go through some of the challenges of solving this problem and the insights that we had. Whether two questions are semantically similar is especially difficult in specialized domains such as medicine, given the nuances in medical language. For example, to tell the questions in the first row are similar requires understanding that being pregnant and expecting is the same thing. Secondly, being infected with coronavirus and having COVID-19 are equivalent. And lastly, going to the hospital is same as visiting a doctor. Similarly, in the second example, it is important to understand that vitamin D3 supplements are very different from hydroxychloroquine in the context of building immunity against coronavirus. So therefore, two of these questions, one asking about the supplements and another asking about hydroxychloroquine, are very different, even though they differ in just a single term, which is the medication. Also, there exists no public question similarity dataset at a scale where these differences can be effectively encoded to learn a similarity function. There are several approaches in the field of ML to address the lack of enough label data, and we list a few of them here. We particularly leverage three of these in our approach. First, the idea of transfer learning. Second, the abundant question answer pairs prevalent on existing medical web forums such as HealthTap. And third, our in-house clinical labelers that we had at Cura. So given the lack of data, what is a task that is relevant and has abundant data, which would help us provide the model with domain knowledge? So the insight was that whether two questions are semantically similar is akin to asking whether answer to one also answers the other. Consider the example shown here. The answer to a question about high-risk pre-existing conditions for COVID that is shown on the left, the answer to it does answer the question about the risk for someone with asthma. This is shown in the green box on the right. However, it doesn't answer what day-to-day activities are high risk. This is the question that is shown in the red box. Thus, the answers in the answered questions contain a wealth of medical knowledge that is helpful in identifying similar questions, which can be distilled into a model. We therefore want to infuse this medical knowledge into the model using not only the questions, but also the answers. And again, this is only possible because medical web forums provide us a large data set of questions and answers. That said, we still need a good quality medical question similarity data set. And that was our second insight, that whatever we do in the first task design, that is not going to be enough, and we still need a question similarity data set of our own. So before I get into our approach, I wanted to briefly introduce the underlying models that we used. We used the well-known transformer-based architecture called BERT, released by Google in 2018. It is pre-trained on the books corpus and English Wikipedia using a masked language model objective. The pre-trained BERT model can then be fine-tuned on a specific task. In our case, that would be the question similarity task. We also experiment with another transformer-based architecture called XLNet to show that our results hold across other pre-trained NLP models as well, and is not really specific to the BERT model being used. So let's recap what we want. First, we want to imbibe medical knowledge into the model. And secondly, whatever task we design, we should already have a large amount of data for it. With that in mind, our approach consists of fine-tuning the model twice. Initially, we fine-tune a pre-trained model on the question-answer matching task. That is, given a question-answer pair, does the answer answer the question? And this is illustrated in the figure shown on the right. What this helps with is it helps us imbibe relevant domain knowledge into generic models like BERT and XLNet. And because we can use Q&A pairs from medical web forums, we can leverage that abundant data for this task. Secondly, since there isn't an existing medical question similarity dataset, we release one that is generated by our own doctors. To generate this data, we presented our doctors with questions sampled from publicly available crawl of a web forum and asked them to do two things. First, generate a similar question by rewriting the original question in a different way while restructuring syntax and medical details as much as possible. And second, generate a dissimilar question by coming up with a related but dissimilar question using similar keywords. And the answer the answer to the original question would be wrong or irrelevant. You can see a couple of examples in this table. The seed question in the first row asks about when one can have a drink after having an antibiotic. For the similar question, the doctors have added some extra details like a party, specific example of an antibiotic, namely azithromycin, and also changed the phrasing. For the dissimilar question, the doctors still reuse alcohol and antibiotic, but change the intent of a question to diagnosing the cause of patient's vomiting. As you can see, it is not an easy data set for a model to master. So to come back to our model, we perform a second and final fine-tuning on this MQP dataset that I described in the last slide. So let's get to the results. But again, before getting to the results, I would like to let's look at some of the pre-training tasks that we evaluate here. So the first one is what we call QA. In this, we use a publicly available crawl of Q&A from a medical forum called HealthTap, where doctors answer user-posted questions. Along with answers, the questions also have a category label. So in the training set, questions paired with their answer form the positives, while questions paired with random answers from the same category form the negatives. The second task is what we call QQP. QQP itself is a large non-medical labeled corpus of question pairs from Clara, an online Q&A forum. So our training data set consists of similar questions as positives and dissimilar questions as negatives. Lastly, MQP is a dataset consisting of similar and dissimilar medical question pairs that I described in the earlier slides. Note here that QQP task is the same as our final task, namely question similarity, but it is on a generic non-medical dataset. QA, on the other hand, is a related task, but it is on medical data, the domain that we care about. So let's look at some results. In this plot, we compare the model's performances with varying sizes of the final MQP fine-tuning dataset. As you can see from the green and blue lines, BERT plus QA model consistently outperforms the BERT plus QQP model. What we show here is that at least in this particular case, the corpus of the task being medical mattered more than the task being identical to question similarity. So to summarize, training on a related task with an in-domain corpus outperforms training on the same task with an out-of-domain corpus. These are the results we saw earlier using BERT. Next, as shown in the second column, we validate that the same trends hold when we change the base model from BERT to XLN. That is, pre-training using QA boosts model performance more than QQP does. So the third row is, the performance in the third row is higher than the one which is in the second row. Moreover, we also experimented with domain-specific pre-trained models such as BioBERT, SciBERT, and ClinicalBERT that are trained on scientific and clinical data. However, as you can see from the first row, these models don't perform any better than a generic BERT model. We hypothesize that the technical literature and doctor notes that these models are pre-trained on use language very different from the colloquial medical question language that users tend to use online. Lastly, as shown in the last row, the same trend holds across a different Q&A dataset as well, such as WebMD. And by the same trend, I again mean that pre-training using QA boosts the model performance more than QQP does. A natural question to ask is whether we could have replaced the QA task with any in-domain task. To answer this, we create two more in-domain pre-training tasks. In QC, a question along with its category forms a positive, while a question with a random category forms a negative. In the second task that we call AA, initial part of an answer and the rest of the same answer forms a positive pair, while the initial part of an answer with the last part of a random answer forms a negative pair. Let's see how these tasks perform. As you can see from the light blue and orange lines in the plot, models pre-trained on QC and AA both perform worse. For QC, we hypothesize that questions in same category can be dissimilar and vice versa, so the learned representations by the model might be worse. For AA, we hypothesize that the answer language that comes from doctors is very different from the patient language in questions. So again, the learned representations for the questions might end up being worse in this case. Thus, we conclude that task design matters too, and one cannot just choose any task in one's domain to get performance boosts. Let's next go to some error analysis that we did on our models. Here, we start with a question that was labeled consistently incorrect. What I mean by that is when at least 4 of the 5 models trained on different train validation splits get an example wrong, we call that a consistent error. Conversely, when at least 4 of the 5 models get it right, we say the models get it consistently correct. If either of this is not the case, we say it gives mixed performance. So with this, we form some hypothesis as to why that consistent error might be happening. We then tweak the question by changing one language aspect of it at a time. And we then see if the model can now label it consistently correct. However, if it cannot still do this, we repeat this procedure. So in this table, we highlight some examples that different models get consistently right or wrong. This helps us get some understanding of the differences between these models. So in the first example, all the models get it right, as the only difference in questions is question phrasing, namely whether the question is framed as one sentence or broken up into two. The second example contains questions about donuts and their digestion and nutritional value. And these are not too medical in nature. So the QQP model gets it right, since it has likely seen many questions of these form. The third example requires an understanding that equal means similar amount of pain relief in the context of Tylenol, which is unlikely to be learned unless the model has seen data of this form and from the medical domain. And this example is gotten right by the BERT plus QA model. So this suggests that we are able to imbibe medically relevant knowledge into the model using the QA task that we earlier described. That said, the last example shows you what complex examples can do to models. So the last example requires a nuanced understanding of language and medical knowledge. Unsurprisingly, none of the models get it right. Here, I want to briefly touch upon how we tweak the question language to get insights into what the model might have learned. In this example, all the models initially get it wrong. To identify these questions as similar, the models have to understand the semantics, and specifically that 4 feet 8 inches in the context of height represents poor growth. If we change the question phrasing as in the second row, the QA model starts labeling it correctly, indicating that what the QA model was likely misunderstanding was the question's phrasing, but it is able to disambiguate between 4 feet 8 inches being poor growth and the height. In contrast, it is not until we replace I am 4 feet 8 inches with I have not grown, as shown in the third row, that the other models get it right. This supports our claim that pre-training on the medical task of question answering embedded medically relevant information into the model that the other models are missing. Through similar experiments, we found that the model is also robust to spelling errors and also to acronyms and terms not being properly capitalized. So for example, if somebody mentions attention deficit disorder as ADD in small letters, even though add is another word in the English language, the model is able to understand that in the right context. We show a lot more examples in our paper. So if you are interested in these kinds of examples, feel free to check out our paper and the appendices therein. Next, I would like to describe how we use this model to apply it to COVID FAQ matching. So our goal here is to match a natural language user question to a given set of FAQs. So while we realize an answer to a given question is very useful in identifying matches, we simplify the problem in this case to identifying questions in our FAQs that are similar to the user question. This allows us to use our double fine-tuned BERT question similarity model for this task. However, since our model is not trained on COVID data, representations for the word pieces of COVID-related terms are unlikely to have been tuned. We show how some of the terms get tokenized by the BERT tokenizer. And unsurprisingly, this leads to undesirable matching behavior. Therefore, we assume that the users will only ask COVID-related questions in the prompt that we show them and replace terms such as the one shown above with generic placeholder like disease in both the user question as well as the FAQs. So to consider an example, how can I protect myself from COVID-19 now becomes how can I protect myself from the disease? Lastly, we score every user question FAQ pair for every FAQ in the curated set that we have using the BERT model to get similar pairs. So let's see the product in action. Here we show some screenshots of the product live on our website. We deployed our model in Google Cloud Platform using Kubernetes and GPUs. So on the home page, the user sees a prompt about whether they have COVID questions. When they click on that, this takes them to a text box where they can type in their questions, which shows them matched FAQs if we found any in our curated set. If we don't, they can still chat with a doctor from here on. The FAQ itself shows both the source as well as when we last updated it from the source side. This is especially useful in an evolving situation like COVID, since the users can stay informed on when the answer was updated and make conclusions about how they want to weigh that factor in evaluating how much they trust the answer. In conclusion, I'd like to end with our main contributions. Firstly, we release a medical question pairs dataset that is created by our doctors. You can find it on the GitHub link that is posted here. Second, we presented an approach of double fine-tuning for the problem of question-question similarity. Double fine-tuning helps the model cope with data sparsity by imbibing relevant domain knowledge via an intermediate task. We also demonstrated that domain and task design both matter, particularly for medical NLP. So pre-training on a relevant task in the same domain outperforms pre-training on the same task in a different domain. Finally, we deployed our model to help match user questions to COVID FAQs.
That's it from my side. Thank you. Feel free to get in touch with us. We are hiring both for internships as well as full-time roles.